Everything we see includes many things that we cannot see. For example, this plant, it has a trunk, branches attached to it, and leaves on the branches. So what would we see if we split those leaves? Cells. What if we split cells? Molecules. What if we split the molecules? Atoms. What if we split atoms? Indivisible, said the Greek philosopher Democritus. Atomos. It means indivisible in Greek. All things consist of some indivisible little things. Yes, this division process has to end somewhere. That's what we thought was true for thousands of years. However, there is a nucleus smaller than this, subatomic particles smaller than that, and fundamental particles smaller than that. And 17 of them. They are the ones who are truly indivisible. In this video, we will examine what they are one by one. This is an atom. More precisely, the simplest atomic model. It has a nucleus in the center. There are electrons around it, and they revolve around the nucleus in an orbit. Protons and neutrons are located very close to each other in the nucleus. This is the basic model of the atom that makes up the matter we see around us. But this model is incomplete. We thought of electrons as planets revolving around the sun, but actually it doesn't have such a classic move. Quantum mechanics took us from this atom to this atom. The color distribution that appears around the nucleus here actually tells us the probability of the electron being found in each position. We are more likely to find the electron in brighter places and less likely in dimmer places. In some places there is none. So we moved from saying that the electron is definitely here and moving around like this to saying that the electron must be around here somewhere. The uncertain world of quantum mechanics has led us to probabilistic and not so intuitive results. One of the most important results that quantum taught us was wave-particle duality. We can talk about particles as billiard balls. They were moving at a certain speed in a certain direction, bumping and pushing each other. This was the particle thinking. But subatomic particles are not just particles. They also move like waves. Normally, we expect billiard balls passing through the double slit to form two lines on the opposite wall. According to the particle model, it should be like this. But we have also seen that when we throw subatomic particles, such as electrons or photons, they move just like a water wave. They formed an interference pattern, almost like waves in the sea. But in some cases, they also behaved like particles. Now let's get back to this atom, the classic one. How close the electron looks to the nucleus. However, in reality the situation is much different, even though we can't tell exactly where the electron is. For the simplest hydrogen atom, if the nucleus were only about the size of a golf ball, the electron would be about 1 kilometer away. So the atom itself is 100,000 times larger than the nucleus. So what's in the distance between? Is it just emptiness? Why doesn't the electron fall on the nucleus? Why are protons and neutrons together in the nucleus, but electrons outside? Nowadays we can explain all this and more with a very good tool at our disposal, the Standard Model of Particle Physics. This table, called the Standard Model of Particle Physics, took us from a single atom to 17 different fundamental particles. We group this table, which resembles the periodic table of elements according to their properties. We see that everything is actually divided into two, matter particles and force particles. We call matter particles fermions, and as the name suggests, they actually constitute matter. The second group is force particles, which we call bosons. First, let's look at what force particles are. There are four fundamental forces in the universe. One of them is gravitational force, that is gravity in short. Einstein's theory of general relativity explains how this force works. This is how we understand the movement of planets and how space-time bends around a black hole. The other is electromagnetism. This force exists wherever there is electricity. Many of our technologies have improved thanks to our better understanding of electromagnetism. Just like gravity explains the orbit of planets around stars, electromagnetism explains the movement of electrons around the atomic nucleus with the support of quantum mechanics. We learn how atoms bond with each other to form molecules thanks to it. The electromagnetic force also has a carrier particle, photon, so light. The photon has no mass and moves at the speed of light. More precisely, we call its speed the speed of light. A photon, like everything else, has a certain energy. Every color we see, from blue to red, is actually composed of photons with different energies. But photons are not just the colors we see with our eyes. In fact, this is a very small part of the electromagnetic spectrum. Radio waves with much lower energy, microwaves and infrared are another part of this. There are also high energy ultraviolet rays, X-rays, and even higher energy gamma rays. In fact, what we mean by radiation is ionizing radiation, which is exactly these high energy photons. Because when these photons hit an atom, they can affect the electron there. If the energy of the photon is too low, nothing happens to the electron. But if it is high, it can move the electron to the next energy level. In fact, if the energy of the photon is much higher, it can remove this electron from that atom. So it ionizes. So photon is the carrier particle of the electromagnetic force. Therefore, one of these four particles is a photon. We denote it with the gamma sign. Another force is the strong force. We owe the existence of protons and neutrons to this strong force, because unlike the electron, the proton and neutron are not fundamental particles. It consists of quarks. The proton consists of 2 up quarks and 1 down quark. On the other hand, the neutron consists of 2 up and down quarks. What holds these quarks together is the strong force. At the same time, protons and neutrons, which are composed of quarks, stay together in this way, and that's exactly why they are responsible for the energy released when we split the nucleus. In other words, from the atomic bomb. You understand why its name is strong force. Just like the electromagnetic force, there is a carrier particle in the strong force. We call this gluon, because it holds the quarks together just like a glue. Because of this strong force, we can never see quarks by themselves. They named them as gluon, as in glue. Even though we only mentioned 2 quarks for the proton and neutron, there are 6 quarks in total. 2 of these are up and down quarks, which also form protons and neutrons. The others are charm, strange, bottom and top quark. These form a group, and we call it generation. Strange and bottom quarks are actually like heavy versions of the down quark. Likewise, charm and top quarks are like heavy versions of up quarks. The fourth force is the weak force. As you might guess from the name, it is not as strong as the strong force. The weak force has another property, being responsible for degradation. Let's take a neutron for example. In fact, neutrons are not stable particles on their own. They have a decay time of approximately 15 minutes. And at the end of this period, one of the down quarks turns into an up quark. Thus, the neutron now becomes a proton, and in the meantime, an electron and electron. Neutrino are emitted. I will talk about what a neutrino is in a moment. But we call the transformation of neutron into proton-beta decay. And the force responsible for this is the weak force. Again, just like the electromagnetic force and the strong force, the weak force also has carrier particles or even particles. We call these W and Z bosons. Among these 3 forces, only the weak force can act on all particles. This includes the neutrino we just mentioned. Neutrinos are very unusual particles. While we watch this video, trillions of them just pass through us. Because they interact very weakly, that's why it is very difficult to detect them. There are 3 different types of neutrinos. We call them flavas: tau neutrino, muon neutrino, and electron neutrino. These 3 flavas can transform into each other during their journey. This is called neutrino oscillation. Their names are not a coincidence. They actually take this name from three other fundamental particles: tau, muon, and electron. All three of these are negatively charged elementary particles, but their masses are very different. The muon is about 200 times heavier than the electron, while tau is about 3,500 times heavier. Muons are also of critical importance for our ability to observe neutrinos. We talked about the four fundamental forces, but only the carrier particle of the three of them. Isn't there a carrier particle for gravity? In fact, we think it is carried by a particle we call a graviton. However, we have not had any observations confirming the existence of the graviton so far, so it remains one of the missing pieces of the standard model. This is one of the biggest problems of the standard model. We can explain the interaction of the three forces pretty well, but gravity is missing. In fact, the effect of gravity on such small scales is extremely weak. But the main problem is that we cannot combine Einstein's general relativity with quantum mechanics. This is why there are efforts to discover quantum gravity theories that we constantly hear about as quantum gravity. We are looking for a single all-encompassing theory. This is still one of the great unanswered problems of physics. Another big problem is the generation problem. The generation we talk about in quarks actually exists in other fundamental particles as well. These are groups of particles that have different quantum flavor numbers and masses, but similar electrical and strong interactions. The first group includes down quark, up quark, electron, and electron neutrino. In the second group, strange quark, charm quark, muon, and muon neutrino. The third group includes bottom quark, top quark, tau, and tau neutrino. The problem here is why there are three generations. Although some claim that there may be a fourth generation, this does not seem possible at the moment. Although string theory provides an explanation for more than one generation, it is still difficult to explain why there are specifically three. So in summary, we have a magnificent model that works great and is extremely compatible with experiments and observations. Standard model. But on the other hand, some of its shortcomings continue to worry us. Before I forgot, the middle of this is not empty either. Guess what's there? H as in Higgs boson. That fundamental particle that gives matter its mass. One of the biggest discoveries of the Large Hadron Collider at CERN. It is also called the God particle by some. But some physicists are also against this name, because in this chart we do not owe everything to its presence alone. Each one has its own importance. They all interact with each other in some way and in turn create harmony. Understanding these rules means understanding everything. Knowing what's inside the circle, understanding what's outside, going further outside, discovering what might be somewhere in between. Here is the standard model of particle physics. Before I forgot, thanks for watching. Don't forget to like, subscribe, and hit the bell icon for more amazing content coming your way. See you in the next video.